we have a set K, we have a submanifold, so K is contained within 2 by 2. It's a closed C2 submanifold. No rank 1 connections. And elliptic. In the sense that the tangent space contains no rank 1 connections either. And the statement was that if we have some u, which is Lipschitz from omega into R2, satisfying this differential inclusion, this implies that the gradient actually holds. Okay, so let's summarize what we learned. So first thing was that there exists a constant C0 bigger than 0 such that determinant of A minus B like this, which followed from ellipticity. We had a bit of a discussion about this because it involved this compactness of a sequence AK, BK, for which we claimed that this was false, and the issue was what additional regularity do we need of the manifold so that we know that we actually get a contradiction. And I looked through that a little bit, and C2 is the right condition, so let's just close that gap a little bit. So we considered AK, BK such that this was false so for any constant C, so the determinant AK, or to be more specifically, this thing was false, was less than or equal to damn it. 2 to the minus K, AK minus BK squared. We divided through by AK minus BK squared and formed this matrix, let's say MK, which is equal to AK minus BK over AK minus BK. And this inequality meant that determinant of this guy was less than 2 to the minus K. And by compactness passing to a subsequence, which we're not going to relabel, this thing will converge to some M. K goes to infinity. I have to write this passing to sub, not relabeled. And our claim was that if our subsequence is such that AK tends to some limiting guy A, which we can do because we're doing everything in a compact subset because we're taking a Lipschitz mapping, then actually this M will belong to the tangent space at A. And contradiction because from this fact we know that the determinant of the limiting guy is equal to 0, so it's rank 1. Yeah, that's how we argued. But this is the point you guys were questioning me on, and I didn't have a good explanation. Let's look at it now. So to see, let me give the name. Let's call that star. So to see star, let's take, so this is a C1 submanifold. We have charts. They are, so again, it's a C2 submanifold. We have charts. There is a chart which contains this point A, and therefore, for all large enough K, it's inside the image of this. It's inside the image of this chart. So we can do everything in one chart. So take chart phi, and from some subset of Euclidean space, whatever the dimension is, we don't care. What should we call the set? Let's call the set U into the manifold M. And of course, it's a C2 chart. So there exists AK, BK belonging to U. Yes, it's manifold K. Thank you very much. Such that phi equals A. Like this. Then let us see what we have going on. So when we consider this expression here, MK is like phi of AK minus phi of BK over phi of AK minus phi of BK, like this, right? And then this thing, because we have C2 mappings, we can use Taylor, and this is like phi of AK. And then I'm gonna write plus minus O of AK minus BK squared, right? Just a direct application of Taylor's inequality. And the same thing here. So this thing is like phi of A prime AK minus BK plus or minus some. So are you happy with the capital O notation, meaning an error which scales like this thing? You know, this just means that there is some constant in front here, and then the actual scaling is given by this thing. Is everyone here okay with that? Thumbs up with that, if that's familiar with you. If you're okay with that. Yeah, okay. Like this. And let's factor an absolute value of AK minus BK throughout this. So then we're going to have phi k, AK minus BK over AK minus BK, and then plus or minus this thing, yeah, over like this. Everyone happy? Yeah. Now, the denominator phi prime of AK, we can assume it's non-zero because we are taking a parameterization. These things are designed not to vanish at any point. So as we let AK tend to BK, this thing will become negligible compared to this thing. And what we'll end up having is just an error which is of order AK minus BK. That's my claim. Okay. So then that thing is itself just like phi of AK ak minus bk over ak minus bk over this thing, phi of ak prime, absolute value, plus error of order absolute value ak minus bk, like this. Yeah. Just because for small enough ak minus bk, this thing can be absorbed into this, it's going to be less than half of this. Yeah. And therefore, we'll have just this thing divided by something which is basically of order 1, which gives us this error. At least to deal with that thing, and to deal with the fact that this thing is almost this thing. We just do the algebra, which just this thing minus this thing is less than this error. So we apply the triangle inequalities a few times, and we get this thing. Yeah, and we have that it's C2. So as we let ak tend towards infinity, as we let k tend to infinity, phi prime of ak is tending towards phi prime of a. This thing is tending towards some fixed vector. This thing is tending towards 0. So in the limit, we will have that this thing is phi prime of a applied to some limiting vector w. Well, that's it, just some w for some w in whatever space we are in. We haven't decided the dimension of the manifold. All right, so dimension of k, like this. And that thing is indeed in the tangent space of k at a. Yeah? So C2 is enough to allow us to have this sequence of vectors or sequence of matrices given by ak minus bk, or absolute value ak minus bk will indeed tend towards the tangent space. And all right, so from C2, we are going to be able to get Holder. What we were able to do then was use the fact that determinants can be written as a divergence, which we've seen several times, and we took some difference quotients of the following kind. So we let UH of x, so this is h of x, be u of x plus h times ej minus u of x, like this, over h, where j was one of the directions, like this, yeah? And then take a test function phi of compact support, and then because the determinant can be written as a divergence, we can write that the integral of the determinant of the gradient of UH of x acting on this test function is equal to 0. Yeah, because this guy which ultimately writes as a divergence will be a vector field which vanishes on the boundary of the region. So it has to be 0. Yeah? And then, so let's put the 0 on the other side. And what's this? This is the integral of determinant. We put the gradient, we have even the right to subtract a constant from this if we want to, and let's do that because it's going to be useful later. So let's write this. So this minus lambda, for some lambda we choose later, times the test function, the gradient of everything. Do I have the right number of brackets? Gradient, and like this, dx. Like this. Okay, so then we apply the product rule. We have the determinant on the guy like this, times phi, and then we have putting the determinant on the second thing, u minus lambda, and then this tensor product like this, d of phi dx. Not about the x. This. We broke it up using the fact we can break up the determinant with this formula. Which again, I'm not giving myself enough space for. Ugh. Okay. So we applied this, and we have this. If I can, plus a cofactor of this thing. And then determinant of this thing just is 0 because it's a rank 1 matrix, so that's all that we have left. Okay. And the real power of this is that we can control this by this. This is the higher order term by a lower order term, and this thing we can control and use to bound above the norm of this thing squared. Yeah? That's the point of the previous inequality. So we have that. And on this side, we apply Cauchy-Schwarz inequality. There's a constant which comes from the fact from our basic inequality that we know that a minus b squared is less than constant c0, that of a minus b. So this constant comes in here, and some other constants, perhaps just from other things, but ultimately we get this. So we are going to apply the Cauchy-Schwarz inequality here. This thing is just has the same norm as the actual gradient because it's just perturbing the coordinates around. So then this thing is du phi squared like this, 1/2, and then this thing is this thing. Over 2. Then we divide through by this thing, and we finally get this thing here, that the L2 norm of this thing this is looking more and more like a K, and it's supposed to be a H, is less than this thing. And as we saw before, this means that we have these difference quotients are uniformly bounded because these difference quotients are bounded in L, well, actually they're bounded in L infinity because we have a Lipschitz function. Yeah? So then this implies that we actually have that the jth derivative has a Sobolev gradient. So the jth derivative belongs to W12. This is so it's J is arbitrary, which implies actually that the gradient belongs to W12. So actually we now have that. Let's write it like this way. For j equals 1, 2, which implies actually that u belongs to W22. We've gained a whole Sobolev gradient. Yeah? That's where we were. Everybody happy? Yeah? Cool. All right, so now look at this and let us pass to the limit as h goes to 0 from this inequality. So from this inequality, then we then have that the gradient of the jth partial, like this, times L2, is less than the integral of omega of the jth partial minus lambda. Again, we still have to choose lambda. We can choose it to be anything we want, times this thing. Yeah. Now we're going to take phi to be a test function on a ball. So pick ball B of x0 within our domain. Actually, make sure it's got twice the radius inside our domain, and let phi be compactly supported inside the ball of radius 2 of this, and phi is identically equal to 1 on the ball of radius 1, or the ball of radius r, x0. So if you look sideways onwards, there's no straight line. If you look sideways onwards, it kind of looks like, well, it can, less steep than that, it can look like this. Right, where this thing is height 1, and this is radius 2, right? So if this is from, okay, so this is 2r in radius, and this is like x0 right here, yeah? So in particular, note that the L infinity norm of this guy is of order r to the minus 1, because we have to raise from 0 up to 1 in something which is of size r. So we need the L infinity, well, we can't help but have the L infinity norm of the gradient be at least of order 1 over r. Yeah? Oops. Like this, yeah? And then take lambda to be the average on the ball of radius r over 2. So take to be the average on the ball of radius r over, r over 2 over 2r of x0 of our partial gradient. Oops. Of our partial gradient of u comma j dx, like this. Yeah? Then, if we put those pieces together, what do we know? Well, this thing will give us that the integral on the ball of radius r0, x0 of the gradient of the partial with respect to j squared dx. This thing will contribute, if we pull the L infinity norm out, it'll contribute constant r to the minus 1. And then what's left will be bounded by the integral of the ball of radius 2, r0, 2 of r at x0, of this thing, the jth partial, minus the average of the jth partial. So this is the notation for the average on the ball of radius at x0, 2r at x0, like this, squared dx. That thing will follow directly from that thing with this choice of test function. This is, this was right at the end, speaking quickly, but well over time, but this is exactly the reverse of the Poincare type inequality we talked about before. Poincare inequality, typically we control the function minus its average by the integral of the gradient. Now it's the reverse. Yeah? And we're going to use that because this guy itself is controlled by our sublaw of Poincare inequality. So recall our sublaw of Poincare inequality that if we have a ball of radius whatever, I think I might as well just put the same function, u comma j to 0 squared dx. Let's take the average, and let's take 1 over 2. And this thing is controlled by some constant times this radius r. And then here we're going to have the average in the ball of radius. So we're doing some 2r, not r. This, and here we're going to have the gradient of j, and then to some particular power. I'm going to write down q. We haven't used it yet, q for the time being, and we'll see what q has to be, right, for the right choice of q, right? And what are these correct exponents? So we found that we control the p power by the other way around. We can control the p power we can control the higher power by the lower power, and the higher power was given by anything which was just below the Sobolev embedding constant, right? So cool, if we have, let me see this, make a sentence first, for the right Q. Okay, so recall, the Sobolev embedding limit was this, n times p, and n minus p when p was less than n, right? And if we had anything which was anything which was less than this thing, we could control this power by this power, yeah, where p was on the right-hand side, yeah? So in our case, let's see how low we can go for our Q to be able to control this L2, yeah? So let's see what happens, what we would need if P star was equal to 2, yeah? So if P star is equal to 2, this is the same as having that 2, so 2 is also the dimension of the space, is equal to 2 times P over 2 minus P, which implies that 4 minus 2p equals 2p, which implies that 4 is equal to 4p, which implies that p is equal to 1. Yeah? So if we had the right to apply this Poincare-Sobolev inequality exactly at the critical case, then we could control this by a power 1, where q would be 1. Yeah? But we don't have the right to do that because we can't go all the way up to the p star. We can go anything just a little bit below it, yeah? Which means that we can't go as low as having q equals 1, but for any q which is bigger than 1, then we can control this thing by the q almost 1 norm of the gradient. You look at this for a second, tell me if you're with me here. So, can take Q to be any Q bigger than 1. Because if we did take this Q to be bigger than 1, then 2Q over 2 minus Q will actually be bigger than 2 itself. That's our claim. Yeah? So then we could take something which was just slightly smaller than this, but still bigger than 2, or actually just take something which is equal to 2 and still have this in terms of this. Yeah, I mean, our aim is to take Q as close to 1 as possible yeah. But if Q is bigger than 1, then this is true. Let's just triple or double check it. This is equivalent to 2Q is bigger than 4 minus 2Q, right? That's equivalent, which is equivalent to 4Q is bigger than 4, which is equivalent to Q bigger than 1. So this thing is indeed equivalent to this, yeah? Yeah. Cool. So if we take any such Q, then the Sobolev critical embedding value is bigger than 2, and therefore we certainly can take some number. We can certainly take 2 in this inequality right here. Yeah. If you look back at your Poincare-Sobolev inequality, that's exactly what we proved. All right, cool. So putting this into this, that means we can control this guy by this guy right here. So running out of space, let's try and squeeze that in. So then this thing, so this R will cancel with this R, so this thing will be less than some constant, and then integral average of the ball of radius 2 of x0 of the same thing, du comma j, now to the q, dx, to 1 over q. Yeah? It's embedded inside the statement right here. Huh? So this line through is the average of the ball. Yes. So on both, yeah. And everything I wrote here is nonsense because this isn't the L2 norm. So let's put this in the L2 norm form, like this. And this is the wrong power of r. It's r to the minus 2 if I do it this way, because this is squaring it. So this again, L infinity norm, this is bound by r to the minus 1. If we have it without the square root, then it is r to the minus 2. And then when we square root it, it becomes r to the minus 1 again. Like this. Yeah. And then let's divide by the average of the ball on both sides on this inequality. And then this thing is just directly the statement. Thank you very much, Josh. All right, everybody with me? Yeah? All right, so this is almost a reverse Poincare, almost a reverse Holder inequality. A reverse Holder inequality is as it sounds. So Holder's inequality says that on bounded domains we control lower order p norms by higher order p norms. Yeah? And this is saying almost the reverse. We have an L2 norm here, which has been controlled by an LQ norm, where Q is very, very close to 1, as close to 1 as we like. Yeah? The penalty we pay is that we had to double the radius of the ball. Double the radius of the ball, which adds some technicalities. But nevertheless, there is a moral here that we are gaining more. So what this should kind of, well, what this actually was, the consequences of this, which hopefully should seem a little bit reasonable at the moment, is that we are gaining extra information about how integrable the gradient of the jth partial of u is. So a priori, we just have that the jth partial of the gradient of the jth partial of u is an L2. But this is saying something stronger. It's saying that it's an L2, but it's also on all small balls, or all balls contained within our domain, controlled by a lower order power. And as we know, it's harder to integrate higher order powers, right? So okay, let me erase the board. Think about your last time you taught Calc 1, improper integrals of type 2, integrals that have a vertical asymptote. How it gets worse the faster it blows up, right? Yeah, so generally, it's harder to take things, put them to a higher power and expect them to be integrable. Yeah? And it's definitely not the case that when you take things to a higher power, you can control things by a lower power. Yeah? That's pretty unusual behavior. So, what do we have? We have that if the ball of radius 2r of x0 is contained within our domain, omega, then let's write it like this. No, let's write out the integral form. So then integral the ball of radius r at x0. So I've taken the jth partial, but I might as well at this point just do this, right? Because the jth partial is arbitrary. This thing, average on this ball, 1 over 2, is bounded by a constant of some q bigger than 1, but q is approximately equal to 1. Yeah? That's what we've got. Now, this is the only game in town for us because we don't have a linear equation. So when we did the sketch of elliptic regularity before, we saw that if we have a weak solution of the Laplacian, so Laplacian of u equals 0 weakly, And if we had that, there is an additional derivative of the function by taking partial quotients and passing to the limit, then it immediately follows that the Laplacian of any partial is equal to 0, and then we could apply the whole argument to the partial derivative and keep going and keep going and keep going, right? That was the beauty of the linear equation. So I should say this implies that here we don't have anything linear. This is a nonlinear situation. So we could only apply the Cacciapelli inequality one time. We had this one shot to do this kind of argument, which gave us this. And then you have to work with this. And happily, there is a tool to do this. And that is Gehring's, it's called Gehring's lemma. It's really better maybe call it a theorem. So Gehring was one of the, I don't know how to spell his name. I think it's like this. Gehring was one of the founders of quasi-conformal, quasi-regular analysis, and he proved the following. And he proved this for functions which are in Rn, and we have things in a domain, and he proved this for things that satisfy a pure inequality in the sense that this radius was the same as this radius, which we don't have. We have to have a weaker result where we have double the radius. And that's a typical situation when we try to do these things in PDE or PDE type arguments. However, there are ways around this. These are technicalities that can be dealt with. So sweeping aside all those technicalities, let's just state Gehring's theorem and see how it's useful for us. So Gehring, if we have a function f, which is in LQ of Rn, and for every x belonging to Rn bigger than 0, we have the following reverse holder. Of the following kind, that we can integrate the average on the ball of radius p of x of the ball q dx 1 over q, then this thing is bounded by some constant a times the integral average of the ball of radius x of just the L1 power. Then there exists some p, which is strictly bigger than q inside this range, or actually I could say then for p. So it could be anything inside this. We have that actually f belongs to LP. So the closer this a gets towards 1, the more integrability we have. If a is a massive, massive constant, then this thing gets more and more just a little bit bigger than q. But the point is we can bump it a little bit. Yeah? Now my dream was that this will be the final theorem of this course, and I was halfway into writing out the proof last night, and I realized there's no way I can fit it in. So it's only 13 pages, but when you write it in full detail, it's a lot longer. However, it's quite a nice readable paper, and it's very pretty and surprising that this is true. And the proof is in a sense, not that hard, but how it's working is still not that clear to me. I spent a lot of time thinking about it. So if anyone wants a reading project, this would be something I would offer, because this paper is interesting, and I'd like to understand beyond the fact it is a proof. I'd like to understand how this works better, which I don't at the moment. But let's talk about this briefly in a minute. Let's just see how we can apply this. So the claim is that we can apply this kind of thing to our situation. You know? And you might think, okay, well, that's not entirely correct for lots of reasons. We don't have the same hypothesis. We have this Q which is a bit bigger than 1 and whatever. But the different ball things, the fact from the bound domain, these things are technicalities we can take care of. The fact we have Q bigger than 1 we can take care of. We can just take F to be this d squared of Q. Yeah. And then if we write this inequality, then what is this saying? Then this is of F to the 2 over Q dx 1 over 2 is less than constant. Getting very perfectionistic about what I put on the board. Probably not worth it. 2 times constant of integral average ball of radius 2 x0, and then this will be just F dx 1 over Q, and let's take things to the power of Q on both sides. So then we have Q over 2 here, and we have just 1 here. And then we have exactly a reverse Poincare inequality in the form of this hypothesis, because Q is, again, is very close to 1. Probably a bad choice to have Q in both cases here. Yeah. So since Q is very close to 1, this is still very much improving. This is this hypothesis, right? And this 2 over Q can be as close to the actual this 2 over Q can be as close to 2 as we like, because we have the right to choose Q as close to 1 as we like, right? So in this theorem, we have a small range to bump up the integrability, you know, given by these constants right here, you know? And in our argument, these constants won't get worse as we let Q tends towards 1. So we can take Q sufficiently close to 1 so that when we get the bump from this theorem, we'll push ourselves into more than 2 integrability. Right? So here we have almost L2 integrability, right? Because, again, Q is very close to 1. So Q is as close to 1 as we like. Yeah. And this theorem gives us a definite small bump on the integrability. Yeah. So my claim is that if we take Q sufficiently close to 1, then the small bump that we get from the Gehring's lemma will push the integrability to be more than 2. Josh, you look very confused. So Q is close to 1, but 2 over Q is right. That was my bad choice of Q too many times. Yeah. So yeah, I should have. Or plus, yeah, 2 over q plus this tiny gain that we get from this thing. And it depends on the constants, but in the constants in these arguments, they're not getting any worse. Yeah, actually the constants are getting worse, but not getting worse bad enough. So that's actually more technicalities that would have to be checked to really produce the full detail of the proof. Let's think, are we using... Because we're using the Poincare suburban inequality, and Poincare suburban inequality does notice the different constants. But nevertheless, we do have enough control that we will just be able to bump up into more than 2 integrability for the second gradient. That's how this will work. But this would require more technicalities of checking very carefully how this thing depends on Q. Okay, all right. But anyway, we are not in a position to do those kind of details, so this is just a sketch. So this is how the proof works, that we apply the PDE adapted version of the Gehring's lemma to our second gradient of U, and that gives us and we get that. How over time am I? Okay. D squared U belongs to L2 plus a little bit like this. Locally on omega, like this. Yeah? So this proof absolutely uses the fact we are in 2 dimensions, right? This doesn't have any hope to work in higher dimensions because at this stage we're going to use the Poincare, we're going to use the Sobolev embedding theorem, because when we have more than integrability than the dimension of the space, then the actual gradient then this thing means that the gradient will be Holder, right? If we have the gradient is more integrable than the dimension of the space, then the function is Holder, yeah? So this implies that the U is Holder. And if we give ourselves some letter like this, so R for R bigger than 2, then it will be what? It'll be like like this, the U of X. One minus 2 over R, like this. This is the Holder exponent we'll get. Yeah, so the bigger the R, the stronger this is. Yeah. So we finally do get that the gradient is Holder from this machine. The final step required this bump up of integrability from the Gehring's lemma. Yeah. And this is written incredibly, this is written very concisely in Sverak's paper, but the reason being is that his background is in elliptic PDE, and this is somewhat standard machine. Once you get this kind of reverse Holder inequality, then pushing it through with the Gehring's lemma to get a bit more integrability and get Holder of the gradient is good. But I claimed more. I claimed that if we have K is smooth, then the actual differential inclusion is as smooth as K. and that follows from this too, because once we have that the gradient is Holder, then consider this thing. So if we take the gradient of the jth partial at x, then this belongs to the tangent space of the gradient at x of the manifold. And the tangent space has no rank connections. So recall when we did this stuff about, I'm finishing in a couple minutes. So when we did the stuff about if we have the differential inclusion into this subspace, just the conformal matrices, this implies that we have smoothness because this thing gives us this additional bump of regularity, right? And the U is infinity, it's actually analytic. It turns out that's true for any subspace without any rank 1 connections, that just the mere fact that we have a differential inclusion into that subspace gives us additional regularity. In fact, equivalent, we get as much of a bump of regularity as this. And this follows from the kind of Korn's inequality type stuff we were doing way back in the course, that we can control the higher gradients by the lower gradients in the Fourier transform. So I mean, these are just words that are not going to make a huge amount of sense, but I just want to complete them because, just to complete the story. What this thing can be thought of is now an elliptic PDE with variable coefficients, where the variable coefficients are Holder. So this thing is actually an elliptic PDE of first order, and any differential inclusion into a set without rank 1 connections will form an elliptic PDE of first order. And this thing is like having that the partial with respect to J satisfies an elliptic PDE with these coefficients that change, or into a subspace that changes with respect to the gradient of U, but the gradient of U is Holder with respect to X. So this is a first order elliptic PDE with Holder continuous coefficients. And again, I can't explain well all of that stuff, but let me just write it down. First order elliptic PDE with Holder coefficients. And it's a kind of basic principle with PDE that if you have a PDE where the right-hand side is smooth and the coefficients are smooth, whatever smooth means, then whatever's the highest order of your PDE, you get the same smoothness back for that order of the PDE. So we have that this thing is a first order PDE with Holder continuous coefficients, which will actually imply that this guy, therefore, is going to be Holder. And that's a long story to get that. You have to work pretty hard to get that from these things, but these are classical things in PDE. And then that's like saying the second gradient is Holder, which allows us to further bootstrap, because now this thing is not just Holder, its gradient is Holder. It's now in C1 alpha, and we can just bootstrap and bootstrap and bootstrap as long as we have sufficient smoothness of our differential inclusion of our set K. That's a very, very sketchy run through of how the rest of the proof works. Writing this out fully would indeed take a lot of space, but again, it's somewhat standard stuff for elliptic PDE. So that is where Sverak's theorem, or how Sverak's theorem is proved, and it's a very beautiful natural statement, but it's not. It's starting to be more applied, but it's not necessarily that well known. And as far as I know, that's the best that we know about differential inclusions. This is the strongest thing we know about arbitrary differential inclusions, is this, and it's only for sets in 2 by 2 without rank 1 connections and that not elliptic. And it's kind of optimal for those sets, but potentially, I mean, there could be theorems in higher dimensions, high dimensional sets of in whatever in m by m matrices. There could also be a weakening of the hypothesis of ellipticity, which is something actually I'm working on. So yeah, that's this there. So tomorrow, which is the final video, I'm going to do a kind of a run through, a kind of survey of all the things we've learned about these kind of things, and it'll be your last chance to ask me questions about any part of it. So look over, and if there's anything you particularly want me to go into more detail about, we will, not tomorrow, on Wednesday. We'll do that then. All right. See you all on Wednesday. Have a great day.